Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
Good day. Welcome to Pastor Victor's Academy. I'm very happy you are watching my video, and I believe you will learn a lot from here. In my previous video, I started talking about engineering thermodynamics, and we looked at the definition and we began to look at basic concepts and definitions. So in this video, I want to continue with basic concepts and definitions. So please pay attention as we go on. So the first thing we want to look at is the two different approaches to thermodynamics. We have the classical thermodynamics and we have the statistical thermodynamics. So here we have classical thermodynamics, statistical thermodynamics. So what's classical thermodynamics? It is an approach to thermodynamics that is concerned with gross or overall behavior. Analysis requires simple mathematical formula and the values of the properties of the system are their average values. Then for the statistical thermodynamics, it is an approach to thermodynamics that is concerned directly with the structure of the matter. Analysis requires advanced mathematical methods. Now, for better understanding, here we have a system which may be closed or open, but it has a way of interacting with the surroundings. Here we have the boundary of the system. It does not mean that the system is closed, it's just boundary. You get so this system is interacting with the what surrounding. Now, energy flows out of the system in terms of heat or work. So, assuming we want to measure this energy, now what classical thermodynamics does is that it looks at the average value of energy in the system. So we may have 1,000 molecules of a particular gas in this system. That's if our system is made up of what? A gas. So we don't just begin to look at energy given out by each molecule of the gas. No. What we do is that we take the average value of what? Energy given out by the whole molecules. So we are not looking at what? The contribution of individual molecules and summing them up. No, we are looking at the what? Average value of the whole molecule. So it's easy in the sense that with a simple formula you can get the energy that flows out of the system into the surrounding through heat or what? Or work. But for statistical thermodynamics, instead of working with the average value, what do? We begin to look at what? The contribution of each molecule of the gas. So when we're able to find out the contribution of each molecule of the gas, then there are other calculations that will have to be done before we can know the amount of energy that leaves the system, whether in form of heat or in form of work. So this approach requires advanced mathematical methods. We can't get the amount of energy flowing out of this system into the surrounding just by using simple formula. Whereas in classical thermodynamics, we can achieve that. So the next thing we'll be looking at is property. So what's property? It is a characteristic of a system to which a numerical value can be assigned at a given time without knowledge of the history of the system. Example, we have mass, we have volume, we have pressure, we have temperature, and we have energy. So that's property. Now, for example, here's a system. It was initially at state A. Then it eventually arrived at what? State E. But we have three different parts. Here is the first part, comprising of different processes. Then it arrived at state E following this part. We also have another part that is directly to state E. Then we have another part getting to state F before arriving at what? State E. Now, assuming we want to know the pressure of the gas or the volume of the gas or the temperature of the gas at state E, the only thing we need to do is just to know the volume or the temperature, then we can tell what the pressure would be. Or we know the pressure and temperature, then we can tell what the volume would be. So that's why it's called property. We can assign a numerical value to it, irrespective of what the path it follows to arrive at that state. We may not know the history. History meaning that we may not know the processes that brought that system to that particular point. But because we already have information about the system, we can assign a value to the what? To the pressure. If what we are looking for is volume, if we already know P and T, that's pressure and temperature, we can assign a value to what? Volume, because the process that brought the system to that point does not determine the value of the property. Instead, what determines the value of these quantities is the state the system is in. Assuming the system is in state F, what we need to know is, okay, assuming we are looking for pressure, what's volume, what's temperature, we can assign the value. Assuming we are at state B, what's volume, what's temperature, we can get pressure. So that's why it's called what? Property. We don't need to know the history of the system. So examples of property, we have mass. Mass is a property of a system. Volume is a property of a system. Then pressure is a property of a system. Temperature is a property of a system. Energy is also what? A property of a system. Yeah, so mass, volume, pressure, temperature, energy. These are what? Properties of systems. That takes us to the next thing, intensive and extensive properties. For intensive properties, their values for an overall system is not the sum of their values for the parts into which the system is divided. So assuming we want to measure the pressure of a system and we have the system splitted into three parts. Now we cannot say the pressure of part A plus the pressure of part B plus the pressure of part C. That's PA plus PB plus PC is equal to P system. That will be wrong. With the pressure of a system is not measured that way. So information about PA, that's in a case where pressure is evenly distributed, just knowing PA is enough. In other words, PA is equal to PB equal to PC equal to P what? System. That's what it is. So where pressure is evenly distributed, this is how we get the pressure of the system. Just know the pressure of a part of the system, then that becomes the pressure of what? The system. Now the same thing applies to what? Temperature. Assuming you have a pot of water on fire and it's boiling, you don't assume the pot is divided into three parts. Then you measure the temperature of this part, measure here, and sum up and say that's the temperature of the water in the pot. It's not true. In a case where temperature is evenly distributed, that's the whole particles have the same temperature. What do? Just put your thermometer in one place. That gives you the information about the temperature of what? Of the water inside the pot. So you don't say you measure here, you measure here, then you sum up. No. You measure one place and that gives you information about what? The system. So I said here their values are independent of the size or extent of a system. Examples are temperature, pressure, and specific volume. Now let's look at the next one, that is extensive properties. Their values for an overall system is the sum of their values for the parts into which the system is divided. Now look at mass, look at volume, look at energy. If you want to measure the mass of a system, you don't just measure the mass of a part of the system, assuming the system is divided into parts. You can't say because you measured the mass of a part of the system, that is the mass of the entire world system. No. Instead, you say Ma plus Mb plus what? Mc. That gives you the mass of what? The system. So in the case of pressure, Pa plus Pb plus Pc is not equal to Ps. But in the case of mass, Ma plus Mb plus Mc is equal to what? Ms. So information about a part of the system is not enough to know about the whole system. Now, the same thing applies to what? Volume. Know that specific volume is different from volume. So volume is an extensive property. If you want to measure the volume of a system, you can split the system into parts, measure the volume of each part, and sum up. So you'll be having VA plus VB plus VC equal to volume of what? System. And it also applies to what? Energy. The energy each part of the system produces, you sum everything, gives you the energy of what? The system, or the energy the system is generating. So you can't say a part of the system produce this amount of energy, so that's what the whole system is producing. No. Energy is an extensive property. So you must know the amount of energy that is produced in all the parts into which the system is what? Divided. Then you take the sum, and that gives you the energy the entire system is what? Producing. So we look at the next basic concept, that's state. So the state of a system refers to the condition of a system as described by its properties. By providing the values of a subset of the properties of a system, the state can be specified. So when any of the properties of a system changes, the state changes. Now take for instance, we have here state 1. It's state 1 because we have the properties, we know the properties, so we can label it state 1. But what happens when pressure changes? Or what happens when temperature changes? Automatically, the system is in a new what? State. As long as we have 10 Newton per meter square, 5 meter cube, and 300 Kelvin, we are still in the same state. But the moment any of these properties changes, we've left this state, we've entered a new state. So here we have state 2. Pressure changed from 10 Newton per meter square to 15 Newton per meter square. But volume still has the same value. Now the question is, what will happen to temperature? Will the temperature remain the same? No. Why? The state has what? Changed. Because pressure changed. So assuming this is a system that is made up of what? Gas. We'll have the formula P1V1 over T1 equal to P2V2 over T2. So you can see from this formula that because pressure increased, temperature will have to do what? Increase. So because pressure changed, temperature will change. Now, pressure increased, volume remained fixed. So in that case, temperature will also what? Increase, so that this condition will be true. So the state of a system is described by what? Its properties. Another thing is steady state. This happens when the properties of a system remain the same with time. So if the properties of a system don't change with time, we have the same values for the properties for a particular period of time. Of course, it's in steady state because the properties do not change. That takes us to the next thing, process. It is a transformation from one state to another. So when I'm leaving state 1 and going to state 2, it is called process. So the process is a transition from one state to the what? Other. Now, in a situation where a system moves from one state to another one and to another one, of course, we'll have two processes and three what? States. Here is state 1, state 2, state 3, but we'll have how many processes? We'll have 2. Here is the transition, first transition and second transition. So the next thing we'll have is cycle. What is a cycle? It's a series of processes whose end states are identical. That is, the process begins and ends at the same state. Now, here is a cycle. Why is it a cycle? Let's assume we started from state 1. We have the first process leading us to state 2, second process leading us to state 3. Then like that, we got back to state 1. This is what? A cycle. Why? We started from state 1, then we came back to what? State 1. So we'll have the same properties because we came back to the same state. So it doesn't matter how many processes we pass through in this cycle, but as long as we came back to state 1, that means the properties we had before beginning the cycle are still the same properties we have when we came to the end of the cycle, because we arrived at the same state. But assuming we stopped our journey at state 3, it is not a cycle because we did not go back to state 1 where we started from. So if I should start from state 2 and arrive at state 2, that's a cycle. If I should start from state 3 and arrive at state 3, that is what? A cycle. But look at this, state 1, time is 0. Then after some time, we had 10 seconds and we are still at the same state. We did not move. That is what? Steady state. That's the difference between steady state and cycle. Cycle involves transitions that brings us back to the same state. But steady state, we don't move at all. We are just there. It's just like someone standing at a place. But in a cycle, you left where you are and came back to where you've been. Now, look at this. So, moving from state 1 to state 2 is not a cycle. It is not a steady state. It's just what? A transition or a process. That's moving from one state to what? Another. Now, don't get confused when you hear the word cycle, thinking it must be a circular movement. No. Now look at this. This looks like the shape of a triangle. It's still a cycle. Why? We move from state 1, go to state 2, go to state 3, came back to what? State 1. That's what makes it what? A cycle. Another concept or definition I want to look at is equilibrium. Now, in physics, of course, we have something like this, the knife edge experiment. Now, this is stable not because there is no force acting on it. Because if we say there is no force acting on it, that's why it's stable. We are wrong. Of course, gravitational force is what? Acting on it. When you move this ruler away from the point of equilibrium, that's when you realize that forces are actually what? Acting on that ruler. So, what is equilibrium? It is not the absence of forces, but when balance is maintained by equality of opposing what? Forces or influences. So in a mechanical setting, we are looking at what? Forces. But in thermodynamics, we can say influences. Okay. So when a balance is maintained by equality of opposing or competing influences. So in other words, the influences are there, but they cancel out. That's why it's called what? Equilibrium. Now, in equilibrium, a system state variables remain uniform and unchanged with time. The state variables remain what? Uniform and unchanged with what? Time. So it doesn't mean the system is in a steady state. Now, the difference between equilibrium and steady state is motion. Now, look at this. We have a fluid flowing through a pipe. Whereas in this case, we have a fluid in a pipe. Now, we have P1, V1, T1. Now, this is steady state if P1 is equal to P2, V1 is equal to V2, and T1 is equal to what? T2. So the properties are the same. However, the fluid is what? Flowing. The fluid flowing means that force is acting in a particular what? Direction. There is the presence of what? A force. But in this case, the particles are not what? The fluid is not moving, meaning that there is no force acting on it. Okay, so here there is pressure along this what? Direction. But the pressure is fixed for a particular period of what? Time. But here there is pressure, but that pressure is countered by an opposing what? Influence, whereby the fluid remains fixed. It's neither moving this way or moving what? This way. So that's the difference between the two. For a system to be in thermodynamic equilibrium, it must satisfy simultaneously the following three types of equilibrium. We have thermal equilibrium. The temperature of the system is uniform and constant with time. So we are looking at the three conditions a system must satisfy before we can say it is what? In equilibrium. First is the thermal equilibrium. In this case, the temperature of the system is uniform. Take note of the word uniform. So at all points in the system, we have the same temperature. Then it's constant with time. So the temperature doesn't change what with time is fixed. Then the second one is mechanical equilibrium. There are no unbalanced forces resulting to movements within the system. So if we have movements within the system, we cannot say the system is in what? Equilibrium. Just as I showed you. Here the fluid is moving, but in this case, the fluid is not what? Moving. The third one is chemical equilibrium. There is no chemical reaction going on in the system. So we don't have reactions going on in the system. The chemical composition is also throughout within the what system. So we're having the same chemical composition. If we have a system made up of gas, we should have the same chemical composition within what the system. Then the system's chemical composition does not change with time. So for a particular period of time, as long as the chemical composition of the system does not change and there are no chemical reactions or there is no chemical reaction, then we can say the system is in chemical what? Equilibrium. It is only under thermodynamic equilibrium conditions that the properties of a system can be fixed. So take note of that. We can only fix the property of a system when it is what? Under thermodynamic equilibrium conditions. The last I want to look at in this video are the intensive properties that are particularly important in engineering thermodynamics. So we have them: specific volume, we have pressure, and we have temperature. What is specific volume? This is the volume occupied by the unit mass of a what? Gas. So in other words, volume per unit mass. Now it is the reciprocal of density. So we're having V equal to 1 over what? Density. So the reciprocal of density is called specific volume. The SI unit is meter cube per kilogram. So if you are asked to calculate specific volume, you have V equal to what? 1 over density, where the SI unit is meter cube per what? Kilogram. So when solving problems, make sure you know what your V stands for, whether it's talking about volume or specific word volume. So in thermodynamics, we usually use the uppercase letter for volume and the small case letter for what? Specific volume. So if we want to calculate the mass of a gas, knowing the density, we do the volume integral of the what? Density. That's integral of density with respect to what? Volume, that's dV. The next one is pressure. This is defined as force per unit area. So the amount of force acting on a unit what? Area. The SI unit is Newton per meter square. So where Newton is for force, meter square is for area. Now take note of this. We have 1 Newton per meter square is equal to 1 Pascal. Then 10 to the power 3 Newton per meter square is equal to 1 kilo Pascal. Then 10 to the power 5 Newton per meter square is equal to 1 bar. So you might be asked to use any of these to solve problems. Then we have 10 to the power 6 Newton per meter square is equal to 1 megapascal. So you should know how to convert from one unit to the other. When you're working with Pascal, when you're working with kilopascal, when you're working with bar, and when you're working with what? Megapascal. So you should know the equivalent in Newton per meter square. Then the last one is temperature. This is a thermal state of a body which distinguishes a hot body from a cold body. So we're able to differentiate a hot body from a cold body with what? The temperature. So it is the thermal state of a body which distinguishes a hot body from a cold body. Then the SI unit is Kelvin, written as K. So temperature can be calculated or required in different units. So we have T degree R, that's the Rankine. Then we have T degree Celsius. Then we have T degree F. That's for what? Fahrenheit. Now this is equal to 1.8 T in Kelvin. Then this is equal to T in Kelvin minus 273.15. Then this is equal to 1.8 T in degrees Celsius plus 32. So you can see the relationship. T in degree R is equal to 1.8 T in Kelvin. T in degree C is equal to T in Kelvin minus 273.15. Then T in degree F is equal to 1.8 T in degree C plus what? 32. So when you know your temperature in Kelvin, you can just multiply by 1.8 and that gives you temperature in what? In Rankine. Then when you know your temperature in Kelvin, you subtract 273.15 from it. It gives you your temperature in centigrade. Then when you know your temperature in degrees Celsius, that's in centigrade, you do what? You multiply it by 1.8 and add 32 to it. It gives you your temperature in Fahrenheit. So finally, we want to look at the first law we have in thermodynamics, which is zeroth law of thermodynamics. It states that if two systems are in thermal equilibrium to a third system, then they are in thermal equilibrium with one another. This is just simple logic. If system A is equal to system B, that's in terms of what? In terms of temperature, and system B is equal to system C. What does it mean? A equal to B, B equal to C. It means that A is equal to what? C. So if system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, it means that system A is in thermal equilibrium with what? System C. So we have A equal to B equal to what? C. So the three systems are in thermal equilibrium with one another. So we've come to the end of this video. Please do well to like, comment, share, and subscribe. If you find my video very helpful, please do well to share. I want to help more students. Thank you so much for watching. Lord bless you.